Hey guys, so welcome to this online Math 200 lecture. This lecture is over chapter 6, which goes through discrete probability distributions. So this chapter has two different sections, and we're going to start with section 6.1, which goes through discrete random variables. So a random variable is just a numerical measure of the outcome from a probability experiment. Its value is going to be determined by chance, since it's from a probability experiment. And random variables are typically denoted using letters like capital X. That's typically what you're going to see in terms of notation. So let's look at an example here. So let's say that let's say that we flip a coin 2 times. The outcomes can be any one of these four things. We can either get heads and then heads, heads and then tails, tails and then heads, or tails and then tails. So instead of being interested in some particular outcome, we might be interested in the number of heads that we obtain when we flip 2 coins. And the outcome is numeric, meaning we either get 0, 1, or 2 heads, and that outcome is called a random variable. Now we have two different types of random variables. We have discrete random variables and continuous random variables. And we tell these apart just like we told apart discrete and continuous way back from chapter 1. So a discrete random variable has a finite or countable number of values. The values of a discrete random variable can be plotted on a number line. So basically whole numbers, that's kind of how you want to think about this, countable things. Continuous random variable can take on infinitely many values, meaning that it can take on a value of 1/2 or 1/4 or 1.5 or 1.75 or 1.216. So the values of a continuous random variable can be plotted on a line in an uninterrupted fashion, meaning that basically we're shading the entire number line instead of just shading particular points. So let's look at these examples here and let's decide if the random variables that are given in these situations are discrete or continuous, and then let's go ahead and state the possible values that could be taken on by that random variable. So for A, we want to talk about the number of light bulbs that are going to burn out in a room that has 10 light bulbs. So we can't have half of a light bulb burning out. We could have no light bulbs burning out, 1, 2, 3, or we could have up to all 10. So this one's going to be discrete because we can count the values that X can take on. So X could be 0 light bulbs, 1 light bulb, 2 light bulbs, all the way up to 10. Now, if we talk about the number of leaves on a randomly selected oak tree, again, we're not going to have half of a leaf. We're just going to be talking about number of leaves, so we're going to talk about 0 leaves, or 1 leaf, or 2 leaves. This one does not have an upper bound on it because we're not really sure what the upper bound on the number of leaves on an oak tree might be. We put an upper bound on there because we only have 10 light bulbs. So we know that it's going to be somewhere between 0 and 10. Now for C, we talk about the length of time between calls to 911. This could be measured in any number of ways. It could be just in whole minutes. It could be in minutes and seconds. It could be like 5.23 minutes, something like that. So this one's going to be continuous with some time that's greater than 0. Or you could really say greater than or equal to 0 because you could have no time between calls to 911. Now, if it said the number of minutes between calls to 911, then that would be discrete because you're talking about a specific number of minutes. So it could be 0 minutes or 1 minute or 2 minutes. But since it just says the length of time, it's not really specific about what increment of time that we're actually talking about. Now, we've looked at probability distributions before, and really what they do is just provide possible values of a random variable x and corresponding probabilities. Now, probability distributions can look like any number of things. It can be a table, a graph, a formula. We're going to take a look at a couple of rules, and then we're going to look at some probability distributions or some distributions and decide if they're probability distributions or not. So these rules should look pretty similar to what you saw back in chapter 5. Really, all of the probabilities, when you add them up, have to equal 1. That's one very important thing. And then all of the individual probabilities have to be between 0 and 1. 1 meaning that the event is certain, 0 meaning that the event is impossible. We can't have negative probabilities. We can't have probabilities that are larger than 1. and we have to make sure that when we add everything up, it equals 1. So let's take a look at a couple of examples, and we want to determine if the following are probability distributions. So if we take a look at this example, the first thing we want to look for is we want to make sure there aren't any negative numbers. We want to make sure there aren't any numbers that are larger than 1. We're all set there. But if we take this and we add up all of our values, you actually end up with 0.97. So this one is not a probability distribution because we don't have 100% when we add everything up. If we take a look at this example here, they've changed one of the values, and if you notice, the corresponding probability for x equals 5 is a negative value. We know that this is not possible. We cannot have a negative probability, so this is also not a probability distribution. If we take a look at this last example, though, we have something that looks very similar. We don't have any negative numbers, we don't have any numbers larger than 1, and when we add everything up, it does in fact equal 1. So this is going to be a probability distribution. Now, a probability histogram is just a histogram where the horizontal axis is going to correspond to the value of the random variables, and the vertical axis is going to represent those probabilities. So this looks a lot like a frequency or a relative frequency histogram way back from chapter 2. Now we have formulas for the mean and standard deviation of a discrete random variable, and the mean is pretty easy to find by hand. I'm also going to show you in just a couple of slides how to find it using StatCrunch as well. But in order to find the mean of a discrete random variable, all we have to do is we have to take the values of x, which are the values of the random variable, and we have to multiply it by the corresponding probability. And once we've multiplied the two, we just add everything together. That's what this summation symbol is here. This is sigma. So if we take a look at this example here, we have the number of DVDs that a person rents from some video store during a single visit. So we have values between 0 and 5, and then we have these corresponding probabilities right here. So if we want to find the mean of the probability distribution, all we're going to do is we're going to take the values of x, multiply it by the probabilities, and add everything up. So if you take a look here, we're taking 0 times 0.06 plus 1 times 0.58 plus 2 times 0.22, and so on. And I'll let you guys go ahead and do this in your calculator. I'll give you a few seconds to try that. And hopefully you came up with a value of 1.49. Now, it's not really too difficult to do when you have just a small number of observations, but one thing I want to point out is if you were given maybe 50 different values of x, this could be really, really tedious. So what we want to do is we want to rely on StatCrunch. Okay, so the StatCrunch instructions are right here, and I'm going to exit out of full screen for my PowerPoint for a minute because I'm going to pop over to StatCrunch. And in StatCrunch, what we're going to do is we're going to go to Stat, Calculators, Custom. So this is kind of a new thing that we have not gone to before. So let me navigate over to StatCrunch. I have my data already in StatCrunch here. And like I said, I'm going to go to Stat, Calculators, Custom. And then all we do is we select where the values are, which are my number of movie rentals. And I select my weights, which are my probabilities. And then I just click Compute here. And what you'll see is that my mean pops up in this box right here. So this looks a little different than other things that we've seen in StatCrunch, but it works just as well. And we get a mean of 1.49, which is exactly the same value that we got when we did this by hand. Okay, so let's look at what the interpretation of the mean of a discrete random variable is, which is what it actually means. So let's suppose that an experiment is repeated n independent times, and the value of the random variable x is recorded each time. As the number of repetitions increases, the average or the mean value of the n trials is going to approach the mean of the random variable. So in other words, if x1 is the value of a random variable after the first experiment, and x2 is the value of the random variable after the second experiment, and so on, then x bar, which is our mean from our experiment, is found by taking all of our observations and dividing by the number of observations. The difference between our x bar and our mu of x, our mean of our random variable, gets closer and closer to 0 as n increases. So if we take a look at this in kind of a visual sense, we have data here. It represents the number of DVDs rented, so it's kind of that same data that we were talking about. We know that the true mean is 1.49. But if you take a look at this example here, the first observation that we got for those 100 randomly selected customers was just a value of 1. So if we look, we put trials along the x-axis and the average along the y-axis. At the very first trial, we have a mean of 1. And then what happens with the second trial is that we got an observation that was a 2, so together those created a mean of 1.5. And then we got another observation, I believe, of, let's see, 1, 2, another 1, and that brought my mean down a little bit. And then what happens is it kind of oscillates a little bit in the beginning, goes kind of back and forth, and then what you notice is that over time it starts to stabilize and it starts to approach this value of 1.49. So as n increases, we know that our mean of our sample is going to get closer and closer to the true mean. And this is really the law of large numbers, which we talked about last week when we talked about probability, which basically just tells us that as our sample size increases, our results get closer and closer to the theoretical value that we would actually expect. So the mean of a random variable represents what we would expect to have happen in the long run. Another word for this is expected value. So you might have heard of expected value before. Basically, it's going to be the exact same thing as the mean. So we're going to look at an example here. This is a pretty typical example where we have an insurance policy, term life insurance policy. It's going to pay a beneficiary a certain sum of money upon the death of the policyholder. Now, they have premiums that you have to pay annually. So let's suppose that a life insurance company sells a $250,000 one-year term life insurance policy. And what that means is one-year term means that if the person dies within that 1 year, they pay out $250,000 to the beneficiary. If that person does not die within a year, then that person is just out whatever the premium is. So it's issued to a 49-year-old female. $530 is the premium that's paid annually. And we know that according to the National Vital Statistics Report, that the probability that a female that's aged 49 is going to survive the next year is 0.99791, so about 99.791% chance that that person will survive the year. So what we want to do is we want to compute the expected value of the policy to the insurance company. Now, if you think about it, insurance companies, the entire goal is to make money. So we should have a positive expected value if we're talking about how much the insurance company is going to make from this one policy. So if we think about this in a table, our values for our random variable basically are contingent on whether the person survives or doesn't survive. So if the person survives, then the life insurance company doesn't pay out any money, and really they ended up making $530 from that person. Now the probability that that is going to happen is 0.99791, or 99.791% chance, because we know that there's about a 99.8% chance that the person is going to survive the year. Now, if the person doesn't survive, they still paid that $530, but now the insurance company has to pay out $250,000. So the cost to the insurance company is $249,470 total. And again, that's found by taking what they made from that person, which is their annual premium, and subtracting what they pay out. Now, in order to get this probability here, this 0.00209, we know that the probability that the person survives is 0.99791. So in order to find the probability that the person does not survive, really that's just the complement. So all we have to do is take 1 minus this value right here, and we get 0.00209. And if we want to find expected value, we do this the same way that we just did in the previous example, which is just by taking x times the probability of x and then adding those things together. So if we take our $530 times the corresponding probability, and we take our negative $249,000 times its corresponding probability, and then we add those two values together, or in this case, really we're subtracting, we end up with $7.50. So what that means is that over the course of offering policies like this, on every policy, the company makes, on average, $7.50. Now, they're never going to make exactly $7.50. Either they're going to make $530 or lose $249,000. But on average, what happens is they're going to make $7.50, meaning that there are going to be a lot of policies where they don't have to pay anything out and they just make money. There are also going to be some policies where the person does not survive and they have to pay out that life insurance benefit. So on average, they do have a profit of $7.50. Whenever you're talking about expected value for an insurance company, you should end up with a positive value just because the entire intent of an insurance company is to make money. So they would never have basically premiums that are too low that they wouldn't make money on them. Now, standard deviation is a little trickier for a discrete random variable, and I'm showing you guys the formula here, but I'm also going to show you how to do this in StatCrunch. So there are two different formulas you can use. They are identical in terms of the answer that you will get. For the first one, what you do is you take your x and you subtract your mean, you square those values, and you multiply by the corresponding probability. You add all of those up and you take the square root. For the second one, you square the x value first, which is the value of your random variable, and then you multiply by the probability, and you sum those up and you subtract the value of the mean squared, and then you take the square root of that. So again, this formula is pretty ugly, and we're going to rely on technology to do the actual calculation for us, just because it can be pretty tedious, particularly when you have a lot of different values for your random variable. So if we take a look back at our example that we have here with the video store rental, we have the same data, and we actually already found the standard deviation, we just didn't take a look at it. So if we take a look, I'm just going to exit out of full screen view here and go back over here. I'm going to pretend like we didn't already do that just so I can show you guys one more time. This is where we go to Stat Calculators Custom, and then we select the values of our discrete random variable, and we select the weights, which are the probabilities, and we click Compute. 1.49 again was that mean that we found, and then if you look right over here, here's our standard deviation. It's 0.9327, it looks like, if we were to round. So let me go back here for a minute, make this full screen again. So you can see that our standard deviation of our discrete random variable is 0.9327. Now, if you want the variance, if you remember way back from, I think it was in chapter 3, we talked about variance. All you have to do is just square the standard deviation. So in your calculator, you would just take this value of 0.9327 and you would square it, and you end up with a variance of 0.8699. Okay, so now we're going to take a look at section 6.2, which goes through the binomial probability distribution. So there are several criteria that have to be met in order for us to talk about something that's a binomial probability experiment. So an experiment is said to be binomial if these four things are true. So the experiment is performed a fixed number of times. We call each repetition a trial, but the key here is that it has to be a fixed number of times. Those trials have to be independent, meaning that the outcome of one trial has absolutely no effect on the outcome of the other trials. And then for each trial, there has to be two mutually exclusive, or disjoint, we called them from chapter 5, outcomes. There's either a success or there's a failure. And then the probability of success has to be fixed, so it has to be the same for each trial of the experiment. Now, there are a couple of notation things that we're going to take a look at, and then we'll look at some examples to determine whether these are binomial or not. So n is the number of independent trials. P is going to denote the probability of success. So 1 minus p, that would be your complement, is the probability of failure. X is going to be your binomial random variable, and that denotes the number of successes in n independent trials. So let's take a look at this example here. So a player rolls a pair of fair die 10 times. So we have a fixed number of trials, it's 10 trials, and then the number of sevens rolled is recorded. Okay, and if we think about this, let's take a look at our qualifications again. We have a fixed number of trials. Rolling the die once has nothing to do with the second roll. And we have success or failure, either getting a 7 or not getting a 7. And the probability is going to be the same for each trial, meaning that we have basically um, the number x of sevens rolled is recorded. Okay, so, oh, it's a pair of fair die, sorry. I read that incorrectly. I was wondering how you could get a 7 on one die. But for this one, we're looking at a pair of die. So we have 10 times, number of sevens rolled is recorded, so that's going to be the same probability each time. So this one's going to be binomial because all of those qualifications are met. Let's take a look at this one here. It says the 11 largest airlines had an on-time percentage of 84.7% in November of 2001. In order to assess reasons for delays, an official with the FAA randomly selects flights until she finds 10 that were not on time. And then the number of flights that needed to be selected is recorded. Now, I see an issue with this one because we don't know how many flights she has to actually select. She might only have to select 10 flights, or maybe she has to select 100 flights or 200 flights. It doesn't tell us exactly how many flights she selects because we know that she's selecting until she finds 10 that were not on time. So there's not a fixed number of trials, so this is not going to be a binomial experiment. All right, let's look at this example here. In a class of 30 students, 55% are female. The instructor randomly selects 4 students, and the number of females is recorded. So if we take a look at this one, we have a fixed number of trials. We have 4 students. And if you think about this one, this is not going to be independent because we have a fairly small class. So what's going to happen is once the instructor selects one student, she's changed the population automatically. So now there are only 29 students left to choose from. So each probability is going to change. So because of that, the trials are not independent. So we cannot say that it's a binomial experiment. Now, here is what the binomial probability distribution function looks like. And basically, this is just a function that allows us to find the probability of obtaining x number of successes in n independent trials. And it looks something like this, okay? So it's a combination formula. We're multiplying by the probability raised to a power, probability of failure raised to a power. Kind of ugly. It's not actually too bad to do by hand, but if you're doing it for a large number of observations, it can be pretty tedious. So we're going to rely on 2 different kind of ways of doing this. We're going to use StatCrunch in order to find these calculations, and then I'm also going to show you guys how to use tables to calculate binomial probabilities. So a couple of StatCrunch instructions here. This might be something that if you're watching this, maybe you want to take a screenshot of this so that you have it. It's typed up in that StatCrunch user guide as well, but not in quite as much detail. So in StatCrunch, in order to find binomial probabilities, you're going to go to Stat Calculator's Binomial, and then you're going to identify and type in the sample size in the place of n, and then you're going to type in the probability of success, which is p, and then you have to decide what kind of inequality you want. So maybe you want a greater than sign, or a less than sign, or an equal to, or a greater than or equal to, or a less than or equal to. And the next slide does have some hints for determining this, but you have to actually select one of those. And then what you do is you type in the value to the right of the symbol that you selected. And then the probability that is given is going to be your answer. Now that works if you want anything that's less than, greater than, equal to, less than or equal to, or greater than or equal to. But if you want an inequality where you have like a between value, meaning you want x between values of 3 and 5 or something like that, then when you go into Stat Calculator's Binomial, what you'll see at the top is that it defaults to standard. You can select between if you want it to be between 2 values. Now I want to go through a couple of phrases here and the math symbols that kind of correspond with those phrases, because this can be a little confusing. So if you see at least or no less than or greater than or equal to, then you're going to use the greater than or equal to symbol. Now the word at least means that it's either this value or higher, so it's going to be greater than or equal to. If you have more than or greater than, that's going to be a strictly greater than sign without the equal to part. If you see the words fewer than or less than, this is going to be a strict less than symbol. No more than, at most, and less than or equal to all correspond with the less than or equal to symbol. And exactly, equals, or is are kind of keywords that you're trying to find something where you're using the equal sign. So this is something that appears in your textbook as well, but again, this might be a nice thing to take a quick screenshot of in case the wording tends to confuse you a little bit. Okay, so let's take a look at this example here. It says, according to Experian Automotive, 35% of all car-owning households have 3 or more cars. So question A says that in a random sample of 20 car-owning households, we want to find the probability that exactly 5 have 3 or more cars. So we know that our sample size n is 20. We know that our probability is 0.35. That's our probability of success that's given in the context of the question. And we know that since we're looking for the word exactly, we're going to use an equal sign. And we want the probability that x equals 5. So what I'm going to do is I'm going to pop over to StatCrunch real quick. And I'm going to put in all of this information here. So let me move this to the side a little bit. I'm going to go to Stat, Calculators, Binomial, and I apologize, let me scoot this over because it's getting a little cut off. Binomial. And then I'm going to move this so I can see it a little better. I have n equals 20, so I'm going to type that in. I have probability of success of 0.35. And if you look here, I don't want less than or equal to, I just want equal to 5. And if we take a look, the probability that's given right there is 0.1272. I've rounded it in the slide. It's 0.127199, so on. So the probability that we get exactly 5 cars out of 20 that have, 5 households out of 20 that have 3 or more cars is about 12%, or about 13%. Now, this is pretty easy to do this way. It's also not very hard to do by looking at our tables. So I'm going to go over to some tables that I've pulled up here. And this is actually table 3. Okay, so if we take a look at this here, I've outlined in red here the probability that we're looking at, just so it's not so much to digest. What you'll see along this table is that we have our probabilities along the top. So the first thing you want to do anytime you're finding a probability is to locate the probability of success that you're talking about, which in our case is 0.35. And then what you do is you look along the left here, and we have 20 observations or 20 trials. So I'm going to look in this 20 section. And then what you do in the section of 20 is you look for the value that you're interested in, which in this case is we want x equal to 5. So I'm going to go over to 5, and I want to look in my circled red part because that goes with my 35%. And if I look at 5 and 35%, I see that I get a value of 0.1272, which is exactly what I found in StatCrunch. So the table gives you a rounded value. It's a nice thing to use if you don't have technology available to you. For the more complicated questions, I would definitely suggest using StatCrunch, but for the easy kind of values where you have just equals to, or I'm going to show you one in a second that's a cumulative one, you should be comfortable with using those tables. Okay, so we have the same setup here, but now we want to know in a random sample of 20 car-owning households, what is the probability that less than 4 have 3 or more cars? So if we think about this one, we still have 20 trials. We still have the same probability of success. Less than 4, that's going to imply that we just want a strict less than symbol. So we know that we want a probability of x less than 4. So I'm going to go back to StatCrunch for a minute. I'm going to close out of this binomial calculator, although I could have just left it open. And I'm going to go to Stat Calculator's Binomial. I have 20 observations or 20 trials, probability of success of 0.35, and I want the probability that x is less than 4. Excuse me. So if I do this, I get 0.044, which is the value that I've typed here. Now, we can also look up this value on the table. So the thing to kind of keep in mind with our table is that if we're looking at table 3, which is the table that I just showed you guys, these are all exact. So if you're trying to find something where you have an equals sign in your problem, you're going to want to look at table 3. But if you have something where you have an inequality, meaning you have less than or equal to or greater than or equal to or anything like that, you actually want to look over at table 4, which is this one right here. And this is your cumulative table. And what it gives you is basically all of the cumulative values from whatever value you start at to whatever value you're looking at. So again here, I've highlighted where the 0.35 is. I have n equals 20. And if we take a look, really what I want the probability that x is less than 4. And what that means is that since I'm talking about a discrete probability distribution function where it can only take on whole values, meaning I can't have half of a household, I know that I need x to be less than or equal to 3. So what I look at on my table is I take a look over here and I look at n equals 20 and I look over at 3 and I scroll over to my 0.35 and I get that same value that I saw in StatCrunch of 0.04444. So the thing to keep in mind is that when you're looking at the cumulative table, you have to have a less than or equals to. Okay, that's what the value on the cumulative table actually represents. So if you have a strict less than symbol, what you need to do is you need to change it so that it's less than or equal to, and then look it up. So let's take a look at one last example here. In a random sample, what is the probability that at least 4 have 3 or more cars? So we could type this into StatCrunch, and there's absolutely nothing wrong with that. But one thing that I want to point out is that what we found in problem B was the probability that x is less than 4. And what we're trying to find here is the probability that x is greater than or equal to 4. So this is just actually the complement of the previous example. So in order to get this, all we have to do is take 1 minus our previous answer. And we end up with 0.9556. Now at this point, if you want to try this in StatCrunch, I would go ahead and pause it and make sure that you're able to replicate this value. And you should be able to pretty easily by putting in 20 trials, probability of success of 0.35, selecting the greater than or equal to symbol, and typing in a 4. Okay, now we also have a mean and a standard deviation formula for our binomial random variable. And these are two formulas that you do need to know. There is not a way to find this in StatCrunch, so we're going to actually be calculating these by hand. And if you take a look at them, they're really pretty simple formulas. So let's take a look at our example here. We have this same example, 35% of all car-owning households have at least 3 cars or 3 or more cars. And we're going to be talking about a random sample of 400 households. So that means that we're going to go around to 400 car-owning households, ask each household how many cars they have, and record that answer. And what we want to do is we want to determine the mean and the standard deviation for the number of car-owning households that will have 3 or more cars. So if we take a look back at our formulas here, the mean is found by just taking n, which is our number of trials, and multiplying it by p, which is our number of successes, in this case having 3 or more cars. So we're going to take our 400 trials, multiply by our 0.35, and we get 140. So what that really means is that out of our 400 households that we sample, we would expect 140 of them to have 3 or more cars. Now, in order to find the standard deviation, all we do is we take the square root of n times p times 1 minus p. So in our calculators, we're just going to take the square root of 400 times 0.35 times 1 minus 0.35 and make sure that this whole thing is under your root. And you should get a value of 9.54. Now, for a fixed probability of success P, as the number of trials in the binomial experiment increases, the probability distribution is going to become more and more bell-shaped for your random variable. So, as a general rule of thumb, as long as n times p times 1 minus p is at least 10, we can say that the probability distribution is approximately normal. Now, since we have something where we have a bell-shaped distribution, we can use the empirical rule, which was way back from chapter 3, I believe. So we know from the empirical rule that within 2 standard deviations of our mean, we have about 95% of our observations, meaning that 95% of the observations lie between mu minus 2 sigma and mu plus 2 sigma. Any observations that lie outside of that interval are typically considered kind of unusual because it's going to occur less than 5% of the time. So if we look at our example here where we have Experian Automotive, let's say that the simple random sample is conducted and it's found out that 162 of them have 3 or more cars. And what we want to know is if this result is unusual. So all we need to do in this case is we already have our mean of 140, that's what we expect. Our standard deviation is 9.54. So since n times p times 1 minus p is at least 10, we can use our empirical rule, which basically tells us that 95% of the observations should be within 2 standard deviations. So if we take our mean and we subtract 2 times our standard deviation, we end up with a lower bound of 120.9. And if we take our mean and we add 2 times our standard deviation, we get 159.1. Now, we were asked about 162 households, which is greater than our 159.1. So this is going to be fairly unusual if the actual probability of finding a household with at least 3 cars is indeed the 35% that they gave us. So that is it for this week. If you have any questions, please feel free to email me.